The first speaker is Sebastian Vasquez. He earned a BS bachelor's degree in industrial engineering and a master's degree in operations research from Pontificia Universidad Católica de Chile. He then worked for 2 years as a software engineer at a Chilean consulting firm, and he developed routing heuristics. He's currently a PhD candidate in operations research at Carnegie Mellon University, where he works with William Van Hoove on discrete bilevel optimization problem. Thank you for accepting our invitation, Sebastian, and the floor is yours.
Thank you very much for the introduction. Really nice introduction. So, can you see my screen right now?
Yes. Yeah. It looks
I don't
good.
see you.
Yes. It's
okay.
working.
Perfect. Awesome. So, hi everyone. Today I'm going to talk about. Oh, this is. Let me think. Perfect. So today I'm going to talk about our current work on network flow-based cuts for bilevel optimization, which is joint work with Leo Lozano and my advisor, Willem. As you may know, this is what a typical bilevel optimization problem looks like. Just for settling the notation, I'm going to talk about 2 players instead of levels. We're going to have a leader and a follower. A leader will select a variable x, and then a follower will best respond to x with y. Y is going to belong to this set of optimal responses, or response set, which is just a set of optimal solutions to an additional problem, which is parametric in X. And just an example, here we see a graphical illustration of what could be a follower's feasible set. All these dots correspond to feasible responses by the follower giving a leader's decision. And if these are the directions in which each player is optimizing, we are considering in this case linear objective functions. For each x, the optimal response would correspond to the one optimizing downwards, right? So if x provides with a variable with a value x equals 1, then the follower will respond with 1, right? Out of the 3 possible responses that he has. If we intersect these with the leader's feasible solution set, we're going to see that out of all the optimal responses, some of them could be feasible for the leader. So if we filter out all those solutions, the remaining are going to be what corresponds to the feasible solution set of the overall problem, or the bilevel feasible solution set. And naturally, a relaxation that we can obtain is just forgetting about the follower's optimality, and this would lead to the hyphen relaxation, the known hyphen relaxation, in which if we optimize the leader's objective function over this relaxation, keeping the discreteness of the problem, in this case, we would obtain this optimal solution, which on top of, in the case of the continuous relaxation, on top of having an integrality gap, we would also have a gap corresponding to the difference between the optimal solution, the true optimal solution to the bilevel problem, and the optimal solution to the hyphen relaxation. So for the sake of this talk, we're going to focus on linear binary bilevel problems in which all functions, objective functions and constraints are going to be linear, and that yields a follower's objective function that only depends on y. And all variables are going to be binary for the sake of simplicity. We know that these type of problems can be cast through its value function reformulation, in which we intersect all constraints, and then we replace this membership constraint to the optimal response set to this type of linear inequality, if we want, without giving too many details about this value function right here, in which we say that for any feasible x, d transpose y has to be feasible. Y has to be feasible for the follower, and d transpose y has to lie below the optimal value for the follower's problem. We know that this space, or this constraint, if you want, is highly non-convex. So a natural question, which has been answered in different ways lately, is if we can convexify in general these type of sets, and if we can do it, how to do it. So we're trying to shed some light on how which tools we can use to achieve this goal. So overall, we could say that the main challenges for this type of setting is that traditional techniques used in the continuous case do not longer apply here. The hyper relaxation, which is usually the standard for most state-of-the-art solvers, yields usually pretty weak bounds. And on top of that, obtaining a strong dual bounds is usually pretty expensive. So what we want to contribute with this in this work with is we want to work on top of network flow based reformulations that have been proposed lately for this type of problems to model the follower's problem or the follower's value function. But in this case, using them as oracles instead of embedding them into reformulations. To do that, we need to come up with new reformulations that are going to allow us to avoid embedding the networks on the program. And finally, I'm going to show some preliminary computational results, which are mainly give us some idea about how fast they recover the bound that the network provides, and also how we can improve state-of-the-art solvers by including these type of techniques into them. So to start with, let me quickly show you how we're going to build these networks. And to do that, I need to make a brief introduction into binary decision diagrams. So these are directed acyclic graphs that have a root node and a sink node, and they are capable of encoding a set of discrete points, right? So in this case, let's say that we have a set calligraphic X that has the origin and all the canonical vectors. And then this network is going to be built in the following way. We're going to have different layers. Each layer is going to correspond or is going to be associated to each component of these points. And then the arc set is going to be partitioned into 0 arcs and 1 arcs. 0 arcs are going to somehow represent 0 value assignment to that specific component or the component of that layer. And 1 arcs are going to represent 1 value assignments to that component. So that in this construction, each of these points is going to be encoded as an RT path over this network, right? So this 0 point here is going to be exactly encoded by the leftmost path or RT path in this graph. So we take this arc, and then this arc. That path somehow assigns value 0, 0, 0 for all components. If we take the last point, this point is going to be encoded as the path to the right of the previous one, right? So we have 0, 0, and 1, right? So that's the type of encoding we're going to use to represent binary points, at least for the leaders portion. So working on top of what Leo did in his previous paper with Andres Iria and David Bergman, they proposed the following encoding. So let's go back to our running example. In this case, we have an integer program, an integer bounded program. So we're going to, since this construction is made for binary vectors, we're going to come up with a simple binary expansion, logarithmic, right, in which we express x as an affine function or a linear function, in this case, of 2 binary variables, right, x1 and x2. So that we can represent all these x values, 0, 1, 2, and 3, as paths on these 2 layers right here. So we have 2 here, we have 0 here, we have 1 here, and we have 3 here, right, as the sum of these 2 binary variables. And then we're going to complete, or we're going to reach the sink node with an additional layer that is going to represent the value function associated to all those paths that are encoding x values that are giving us the same follower's problem, or a follower problem that achieves the same optimal value, right? So in this case, this x equals to 0 point here is exactly this path, and it evaluates in the value function as 1, right? And it can be merged with this one because it has the same evaluation, which corresponds to 1, which is exactly this path, right? So if you look at this encoding, this exactly encodes the set, the graph of the value function, right? For each x, I'm retrieving in the last layer the evaluation of the value function. And in their paper, they came up with this single level reformulation in which they extended the space with these W flow variables, in which they are forcing W to be a one RT flow on the graph. And then if you look at these 2 constraints, we're seeing here that for each component of X, once it is chosen to be binary, then the flow through all 1 arcs on that corresponding layer has to add up to the value of Xj. And then for D transpose Y, which is the follower's objective function, the length of the chosen path has to be an upper bound on it. So if the network indeed recovers the evaluation of the value function, this is exactly the value function constraint, right? The initial value function constraint. So all this system in this reformulation replaces the value function constraint. So now I'm going to jump into what's the main idea behind this reformulation and why it works. And we're going to use it to exploit the reformulation in a different way. Naturally, if you look at this reformulation, it is parameterized by the network. So if the network grows exponentially large, then this reformulation naturally will increase at the same rate. So we know that the value function reformulation can be written equivalently as this program with a membership constraint, right? So we say that instead of d transpose y being below the value function evaluated at x, we're going to say that x comma d transpose y belongs to a hypergraph of phi, where the hypergraph is just x extended with a real value, and that real value has to lie below the value function evaluation at that specific x value. And a super simple result that would somehow like change the way of modeling the forward value function using exactly the same tools is that any xc value, where c is just a real an extension of the x vector with a real value that lies in the hypergraph of the value function, also has to belong to a convex hull of the hypergraph of the value function. And these type of results have been recently exploited also in a paper I remember by Henry and Martin, and it's pretty traditional usually in decomposable problems or two-stage stochastic problems, for instance. And the nice thing about this is that we can equivalently, without loss of generality, replace or relax the hypergraph membership constraint with the convex hull of that hypergraph of the value function, right? And the nice thing as well is that for this one, we have somehow like a discrete description of the hypergraph of the value function. With this, we can find out ways of outer approximating this convex hull. And that's exactly what we're going to exploit right here. So the new reformulations that we're proposing are two. One is based on optimality conditions from the follower problem seen as a network flow problem, and the other one is based on a feasibility view of the same problem, right? So you can think about this as Bender's optimality cuts or Bender's feasibility cuts or Farkas lemma applied to a feasibility problem if you want. So in the first reformulation, the main intuition to derive is given a binary vector x and an already compiled network. We know that since we're optimizing over the hypergraph of the problem of the value function, we can maximize over the hypergraph to reach the graph, right? That's finally the value that the leader will consider to optimize his own problem. So phi can be written in this case as a longest path problem in which the x component of the network is already fixed by x hat, right? So x hat is fixed, the completion or whatever you need to reach the sync node is going to be exactly the value function evaluation given the construction of the graph, right? So we can take the dual of this, since this is just an LP, where P of D is just the dual cone of the problem, right? This yields this reformulation in which we swap the value function reformulation or the membership constraint with this family of cuts, which we call optimality cuts, right? They come from extreme rays of this dual cone. And in general, they can be separated in polynomial time or polynomial number of steps on the size of the network, of course. And if you look at this cut form, you can pretty much tell that, or you could ask yourself, if no good cuts are already part of these cones. And in fact, they are, right? So you can somehow like split this lambda portion of the array into two components, one multiplying x and a different one multiplying 1 minus x. The constants are going to be absorbed by pi or pi r in this case, right? So indeed, no wood cuts are one possible extreme ray of this cone. Naturally, it will provide a super weak continued relaxation. So we provide a simple procedure that can yield tighter cuts, and that's the one that it's polytime on the size of the network. And the second program comes from a Farkas application to a feasibility program, pretty much the same you would do for Bender's feasibility cuts, in which now if you provide me with X and Y, and you also give me a compiled network, this program right here is telling us that there exists a flow vector that can convexify somehow the X portion of the original vector you're providing me. And then the convex combination of the lengths of the paths you're choosing lies above d transpose y for that value, right? So this is pretty much telling us in an extended space that x comma d transpose y belongs to the hypergraph of the value function, just because of this inequality right here, right? In other words, if the point does not belong to the convex of the hypergraph, then this problem is infeasible. If we take the dual of it, we know that the dual cone is not going to be empty, right? So this gives us the idea that any unbounded direction given by a x-y solution that renders the feasibility problem infeasible is going to work as a valid cut and is going to separate this original point. And this yields the second reformulation, in which we replace the value function constraints with this set of extreme rays from the dual cone of the feasibility problem, which we call feasibility cuts, right? As a difference from the previous cuts, these ones also provide a multiplier for d transpose y. So they somehow include the family of optimality cuts. And these cuts in particular can be separated either by solving the dual of the feasibility problem, or we can also solve a Lagrangian relaxation of it, in which we partially relax some of the constraints. We can guarantee optimality of the remaining Lagrangian relaxation, and we can obtain subgradients of that program by solving shortest paths, iterative shortest paths over the network. And this has been used previously on several work. And finally, the last thing I want to talk about, which is going to be super brief, is about how we can strengthen cuts using this data structure. So let's go back to our running example, and let's look at the hypergraph we're trying to convexify. So let's say that we have a valid inequality, in this case, minus x plus 3y less than or equal to 6, which we can translate into our binarized space, right? So if we replace these coefficients in our network, we can already see that any path length right here is going to exactly compute the left-hand side of the cut, right? So for any path we traverse, we compute all the lengths of those arcs. That's going to give us the left-hand side of the cut. If we want to check how much we can improve the coefficient of one single component, we can go to that layer. Let's say we want to see from this cut how much we can increase the component associated to x2, right? So we can look at this layer right here. We can look at the one arcs, and the one arcs are going to somehow include all the paths that are satisfying x2 equals to 1, right? So we look at all paths using these one arcs right here, and we compute their left-hand sides. We take the maximum of those. If there's a difference with the right-hand side, that's exactly the amount we can increase the value of that coefficient, right? And we can do this component by component. If you want to know how much it evaluates every path using a one arc, it suffices to take the tail, and compute the maximum paths from R to that tail, and then do the same from the sync node to the head of that arc. And that's exactly giving you the maximum evaluation of every path using this one arc. If you do it for every one arc, this is giving you exactly the maximum left-hand side of any solution satisfying x2 equals to 1. And this pretty much resumes into computing shortest paths or longest paths, sorry, from the root node to every node and from the sync node to every node. So this could be relatively efficient. This would be like the final result after 2 iterations, in which we can check that if we modify these coefficients, we achieve a new cut, a new tilted inequality, which, for the sake of the example, this one is fast at defining with respect to the hypergraph of the convex of the hypergraph of the value function. So let me quickly jump into some experiments. These are going to be used on networks that exactly represent all solutions in the graph of the value function. And I'm not going to mention anything related to benchmark instances. I have some preliminary results, but I want to focus on the strength of this approach, on how fast we can recover bounds, and also which type of structure we can exploit with this approach. So I'm going to show you results on 2 families of instances. The first one are instances in which the number of follower constraints are increasing, And a second one is a one in which the follower problem exposes a block diagonal structure, right? So we have a fixed dimension problem for the follower, and then we split the follower into different blocks. In this case, we split into one block, which is the regional instance, 3 blocks, and 5 blocks. We're going to compare the network flow reformulation of Leo Lozano. And then we're going to also use our cuts, the ones that we just derived. And since this type of structure can leverage other type of cuts, we're going to also show them for the sake of reference. And all these cuts are going to be tilted by our previous approach. All implementations details are right here. We set a time limit of 1 hour. So if we look at the instances with one single follower constraint, here I'm showing you the network flow-based reformulation in blue, these target cuts, which are just a reference in yellow, and all the dashed lines represent R cuts, right? So the red dashed line represent the optimality cuts obtained as no-good cuts. So these are super easy to generate. This one is the procedure I talked to you about, in which we provide tighter cuts than no-good cuts. And these are the second family cuts, right? Feasibility cuts. And here I'm showing you how fast each of these methods are capable of recovering the bound of these instances. This right here will correspond to the continuous relaxation of the hyper-relaxation. And the one right here corresponds to the best known solution across all methods, right? So this is somehow like a measure of bound recovery. When the number of constraints is small, given small networks, the exact approaches, or the approaches that consider the whole network in them, are much faster. And this is expected, right? If the networks are small, then you would expect that embedding them is not going to provide a huge overhead, so you should be better off, and you have a full convexification of the value function, or the hypergraph of the value function, on an extended space. But as we start increasing the number of constraints, here we still see that networks are small enough for the complete reformulation to be superior to the other methods, but then we see that it can start somehow like dying already. This target cut approach is an LP-based cut generation approach, so it has the same issues as the reformulation, and we can check that our methods that use the network as an oracle are still performing decently. And then with 4 constraints, these methods just die. They cannot provide any bound within 1 hour, and we're still doing something. And overall, the Lagrangian approach for deriving feasibility cuts is the one that provides relatively better results. If we move to the block diagonal follower, remember that these are followers that are split into different blocks, but the whole dimension remains fixed to 45 variables in this case. I'm showing you, again, with blue, the network flow-based reformulation. In green are feasibility cuts, which are the ones that showed the best results in the previous experiment. And here I'm including one state-of-the-art solver. We have similar results for MIPS, which is another state-of-the-art solver. This is just one for the sake of parsimony in the graph. On a solid line, I'm showing you FLMS. On a dashed line, I'm showing you FLMS if we embed the network flow reformulation instead of the hyper-relaxation. And on dotted lines, I'm showing you FLMS with the addition of feasibility cuts that we would obtain with the same method after executing it for 5 minutes. And then we run FLMS for 55 minutes. So as you can see, whenever we have one block, still network flow reformulation is competitive, or it could be even better than our cutting plane based approach. If you look at FLMS, it's performing right there, but it's not comparable to the cutting plane approach. But interestingly, our method, since it just includes cutting planes and it doesn't extend the variable space, allows to improve FLMS. In contrast to adding the reformulation into the state-of-the-art solver, that one, since the reformulation is large, it hurts the state-of-the-art solver, so it can deteriorate the performance of the solver. If we move to 3 blocks, the problems become more challenging, but you still see the same trend here. The cutting plane approach performs better than the network flow reformulation. And if you look at FLMS, you obtain a boost after adding cuts, and it performs worse if you add the reformulation to it. And for 5 blocks, the trend is pretty much the same, but all methods based on the reformulation just struggle from the size of the networks, where our cutting plane approach is capable of improving FLMS, and by itself, it performs much better because you're not relying on embedding your network. So overall, I want to conclude this talk by giving you some insights of this work and also some future lines of research. First, as you could see from the results, for some instances, especially when the instance require large or multiple networks, our cut approach may recover the bound given by the network much faster than just embedding it into a reformulation. These cuts provide a more natural integration into state-of-the-art solvers since we're not extending the variable space, so we're not truly, or we're messing with, but not that much in terms of how these state-of-the-art solvers generate their own cuts. Something that I didn't show, but you can trust me that this tilting strategy greatly improves the quality of the cuts, especially when your seeding equality is pretty weak, as no-wood cuts. And as I mentioned, we were using exact networks, so we're exactly enumerating somehow all points within the graph of the value function. If the graph is still too large, we can work with approximations, upper bounds of the value function, and we would obtain lower bounds in the overall approach. These upper bounds could be algorithms or heuristics for the value function, or we could use DP type of techniques to merge nodes that are not equivalent, and then finally obtain upper bounds on the value function for all these merged states. And as future work, we would like to leverage a structure in our compilation. The current results do not really exploit the structure of the problem aside from the multiple block follower. But in general, if you have a combinatorial problem in the followers space, we could leverage that using like traditional DP strategies. Also, we didn't put too much work on cut selection. We realized that better seeding inequalities provide better cuts after tilting. We should look into that for sure. Our tilting approach, as you could expect from the explanation, is sequence dependent. So if you make bad decisions at the beginning, it would hurt the approach pretty bad. So defining tilting strategies or smarter tilting strategies is super important in our case. And also something we want to exploit is dynamic compilation. If you embed your network on a reformulation, you're not allowed to modify it without adding new flow variables. So you need to stop your branch and bound tree and then resolve it. See, if you use it as an oracle to derive cuts, you're allowed to modify it, and then your new cuts are going to look at a different network, or they're going to be obtained from a different network. So that's all I got to say for now. I hope I'm not over time.